Hello and welcome to Lecture 3 of Work and Energy in Electrostatics in Phys 1204. In this lecture we're going to get quantitative and start looking at how to calculate electric potential and electric potential energy. The first thing I want to do is remind you that way back in Phys 1104 we saw a general way of calculating work on a particle. When we have a variable force along a curved path, we have to be careful. First of all, we know that only the component of the force acting along the direction of motion does work. And so that's why we use a dot product between the force and the displacement. But second of all, if the force is changing and the direction of the force vector relative to the displacement vector is changing, then we have to think of the path as being broken into many small little bits, calculate the works for each of those small little bits, and then add them together. And in the limit that we let those bits get very small, that turns into an integral, which is precise. So let's now find, for some charge Q2 moving along some path from A to B near another charge Q1, how much work the electric force does on Q2. So note, we're thinking of just Q2 as our system, and either we can think in terms of Q1 doing work on the system, or we can think of the field due to Q1 doing work on the system. Either way we think about it, it's the same thing. And for convenience, I'm going to put my axes so that the origin is at Q1, and that's just so that the R12 vector that points from Q1 to Q2 and which determines part of this force is nothing more than the position vector R of the charge Q2. And now let's think of when Q2 is at some R. At that moment, of course, there's a force acting on it due to 1, which is radially out from 1, and the dr vector would be tangent to the direction of motion. But there's no need to do all this icky geometry and integrate that along the path from A to B, because we've already seen that this work has to be path independent. And so we might as well instead think of this path from A to A prime and from A prime to B. And now we know that the force is perpendicular to the motion everywhere along the A prime to B part. And so if we say the work is just the sum of those two works for the two segments of the motion, the A prime B part just gives us 0, and we're left with this, which is going to be much simpler to calculate. Now, instead of integrating from RA to RB, we're integrating from RA to RA prime, and that's going to be much simpler because the force and the dr vectors are going to be parallel along that whole line, and so the dot product ends up being easy. So let's see that in detail. Everywhere along here, we can talk about an r hat vector, a unit vector pointing radially out from Q1. And in particular, the dr vector is certainly parallel to that. And so we can write it just as a magnitude dr times r hat. And similarly, the force that one is exerting on 2 is in that direction, and so we can write it as the scalar expression kq1 q2 over r squared times r hat. So let's put that together and simplify our integrand. So here's what our integrand looks like when we do that. We can just rearrange it and pull all the scalars out front, and we're left with an r hat dot r hat. But remember that a dot product is just the magnitude of the one vector times the magnitude of the other times the cos of the angle between them. Well, both of those vectors have magnitude 1, and they're parallel, and cos of 0 is 1, and so that whole thing is just 1. Notice that with that dot product reducing just to 1, all of the vector nature of the integrand has disappeared. And so we have a nice scalar integral where I no longer have to worry about the vector nature of even the endpoints of the integral. And as one more thing to simplify further, I'll note that RA prime is in fact RB, the final distance from Q1, And since we're trying to find the work from A to B, I might as well put that back in. While I'm at it, I'll take all these constants, k, q1, q2, and pull them out in front of the integral. And so finally, we just have this integral. That's not exactly the easiest integral ever, but it's pretty close. That will have been one of the first integrals you learned to do, and so you can do that very easily. And this is the result we get for the work carrying Q2 from A to B. Note, in particular, that this work only depends on the initial and final distances between the particles. Nothing vectory is left. All we have are some distances to worry about. Now let's use this to think about the electric potential energy of the pair of particles Q1 and Q2. And since I'm frequently going to be going back and forth from now on between thinking about a system involving only a particle that we're moving around and the work done on it by all the source particles, or equivalently the work done on it by an E field, versus thinking about a system which includes the particle we're moving around and the source particles, I'm going to tend to start splitting the screen in two whenever I do this and showing them side by side to keep them separate and yet be able to connect them. So we now know this work that Q1 has done on Q2, and what we've seen in Lecture 1 is that the work that 1 does on 2 has to equal the negative of the change in the electric potential energy of the system that includes 1 and 2. And so we can immediately write down this change in electric potential energy, where all I've done is take this and multiply through by -1. And now a slight rearrangement makes it look like this. Notice, delta UE by definition has to be a UE final minus a UE initial. And we can just identify. There's the final. Note, it depends on the final value of the distance between the particles. And there's the initial. It depends on the initial separation between the particles. And so we can now read off an expression for an electric potential energy of a system of a pair of charged particles. It must just be K Q1 Q2 over R. Let's just examine some properties of this expression for the electric potential energy. Note something. If we are bringing particle Q2 in from an infinite distance, or effectively just from very, very far away, then the initial electric potential energy was some number over R, and R was very large, and so that is 0. Now, remember where a potential energy is 0. A potential energy is always 0 wherever you say it is. But if we're using this expression, we've already come up with our convention. We've already decided that we're defining the electric potential energy at infinity as 0. There's no reason you can't make another definition, but in practice, this is almost always the most practical choice. Notice something else, and again, I've split the screen between the perspective where both of the particles are in the system and we're talking about the electric potential energy in the system versus the situation where we're talking about the work done on particle 2 by particle 1. So in this case, in the case where both of the particles are in the system, our delta UE was just, which is just UEF. And remember that we take the negative of that to get the work that Q1 did on Q2 as Q was brought in from infinity. And so the work, we could say, of 1 on 2 as we go from infinity into some RF is just the negative of UEF, which is just K Q1 Q2 over RF. It's also worthwhile to briefly think about the sign of this potential energy. If Q1 and Q2 have the same sign, it doesn't matter whether they're positive or negative, but as long as they have the same sign, then Q1, Q2 is positive, and so everything here is positive. We know that UE is going to 0 at infinity, and so we have a 1 over r curve, something like this. And notice we already knew that for like charges, they have higher potential energy when they're close together, and that agrees with this graph. On the other hand, if Q1 and Q2 are of opposite sign, it doesn't matter which one's positive, but if they're of opposite sign, now Q1, Q2 is negative. Again, the potential energy goes to 0 at infinity, but now we have a negative 1 over r curve. And again, we already knew that when charges have opposite sign, they have more potential energy when they're farther apart. And that's what this curve is showing. Although note that the potential energy is always negative, it's simply less negative when r is large. What if we have more than 2 charges? So let's do 3. So here are 3 charges, and I'm starting them off so that Q1 is here. And Q2 and Q3 are each starting off somewhere an infinite distance away from Q1 and far from each other as well. And what we're going to do is we're going to assemble this charge distribution into this final shape. So first we'll bring 2 in from infinity. And we just saw that the work that the electric force does on charge 2, as we bring it in from infinity, is this expression. So we already know that. Note that 3 is infinitely far away, and the force that it exerts on Q2 as we bring it in is negligible, and so we can ignore any work that 3 does on 2. But now we have to bring 3 in, and while we're bringing 3 in, 1 and 2 are already here. And so the work done, which I will call just work 3 as we bring it in, is going to be a sum. It is going to be the work that 1 does on 3 as we bring it in from infinity, plus the work that 2 does on 3 as we bring it in from infinity. But we know what each of those are. They're going to use exactly the same expression. And so in the end, the total work that was necessary to assemble these 3 particles into their final configuration was this sum of 3 works. Well, now we can conclude what the potential energy is, because again, we know that to get the change in potential energy of the system, all we need to do is take the negative of the work done by the electrostatic forces. And so that will give us the change in UE as we bring these particles in from infinity. And that is our UE final minus our UE initial. But since they started at infinite distance, we know that the initial was 0. And so we're just going to get our UE final, which is the negative of the work that the electrostatic force did. And so it's just all of this same expression, but with positives instead of negatives. And so we see that all we have to do when we have more than 2 particles to get our total electrical energy, all we have to do is sum up all of the pairs of the individual electric potential energy expressions. So let's have a question to see how you're understanding this. Here are 2 charges of opposite sign. Charge 1 is staying stationary, and we are bringing charge 2 in from rest to some closer location and also at rest. Think about whether the system of the 2 particles gains or loses electric potential energy, and whether the work done by this external agent is positive or negative.